Thank you. I'm really happy to be here. As I commented over lunch, I made a lot of use of the Concawe well-to-wheel data in the past when I was working on hydrogen scenarios. But today I will talk about green hydrogen, about the electrolysis technology. I'm known to be clumsy with these things, but let's see how it goes. First, I'll talk a bit about one slide about what we're doing at TNO, the research institute in the Netherlands where I work on hydrogen. Then we'll dive into the content, the role of innovation to bring down the cost of hydrogen. We'll shortly discuss the different electrolyzer types that we have, but the main message is in the ambitious growth. What are the limitations in how quickly we can scale up, and those are more generic than technology specific. And I'll end with some conclusions where I include a call to action for this community. TNO is an interesting place to work on hydrogen because we have a lot of different groups working on this. We have geoscientists working on underground storage. We have our oil and gas group looking at the suitability of the infrastructure for hydrogen, looking at the North Sea as an offshore hydrogen location. We have the groups who work on the end use, on combustion engines, on fuel cells, a lot of different departments. But I'm part of the electrolysis group, and we've grown from 10 people in 2 years to 50 people, and that indicates how much interest there is from industry to invest in innovation. And why is this such an important topic? That's shown in the next slide. This is a slide from IRENA. I can really recommend this report, Green Hydrogen Cost Reduction. But what this slide shows is that to go from today's cost of hydrogen to our future cost of hydrogen, and we know that currently the hydrogen is quite expensive, there's quite a need for innovation. And specifically indicated in this graph is the need to reduce the cost of the electrolyzers, to improve the efficiency, and to improve the lifetime. What you can say is that this is really a first generation of electrolyzers, and I'll illustrate that with this graph. This is specifically a kind of high-level roadmap that we made for PEM technology. And the question is always at which TRL level is an electrolyzer. Well, if you look at the first generation, that is today's technology, of course it's at TRL 9 because you can buy the systems commercially. But what you also see in this graph is that we expect that there will be next generations which will have a much improved performance. In the case of the PEM electrolyzers, we expect that the second generation, which is the technology which will be commercial around 2030, will be based on highly improved components, membranes, catalysts, all kinds of components coming from the supply chain, while there's even a third generation which is really about radical innovations in the electrolyzer technology. And the key message is, yes, it's a TRL 9 technology, but only for a first generation. There's a lot of potential still to be developed, but that's still at a lower TRL level. Now there's a lot of emphasis on cost, and I made a very simple calculation of the cost of hydrogen just based on electricity cost and investment cost, and based on 50 euro per megawatt hour and 1,000 euro per kilowatt investment cost, you kind of get this graph where you see about 1/4 is the investment cost, and the largest part is the electricity cost. But this is for 8,000 hours of operation, so nearly full operation. If you look at, for example, 2,000 hours per year, then you see that the capital cost becomes really dominant. And those 2,000 hours, maybe they are exaggerated for the moment, but the reason that we want to go to hydrogen technology is that it helps us in integrating renewable electricity in the energy system. And you can only do that if it is indeed a flexibility technology. And that means that you need to design it for operation only when there is excess electricity, or when there are really low electricity prices. And that means that we really have to bring down the cost of the technology. And that is part the electrolyzer stack, so the core of the technology, but also on the whole system design and the power electronics, we need to make big steps to improve that. View of the time, I'll skip this. Electrolysis is a very simple technology. I mean, we've maybe all done it in the high school, where you have the experiment with a battery and two electrodes, pencils or whatever you use for that, and you can produce hydrogen. If you do that, what you need is a 4.5 volt battery, which means that you have a really low efficiency, because what you would need is 1.5 volt. So if you want to make it much more efficiency than this high school test, what you need to do is bring those electrodes really close together. But at the same time, for an industrial process, it's nice if we have the oxygen and the hydrogen separated. So we need to have an effective separation of the gases. And basically, the different technologies are based on different principles for that separator. It needs to be ion conducting, because you need to close the loop, and it needs to be gas tight for hydrogen and oxygen. And quite a lot of other requirements, chemical stable, mechanically it needs to be thin. But what this does is that it leads us to different technology. So for example, for the alkaline technology, we use a porous material which contains KOH, so is ion conductive. For the proton exchange membrane type, we use a solid polymer which is capable of conducting ions. The solid oxide high temperature process is based on a ceramic conductor which becomes ion conductive at high temperature. And we have other younger kids on the block, let's say like the anion exchange membrane. Looking at some of the differences between the different technology, then what we see is that some of these technologies have less need for scarce materials. The alkaline and the solid oxide in particular do not have intrinsically these materials. I'm saying intrinsically because in some of these technologies we are currently using scarce materials or cobalt, but in principle these technologies can be optimized to work without these materials. Why look at the PEM? Because it has a high power density and could be very flexible. So for example, if we're looking at offshore hydrogen, this is a very interesting technology. Specific for the solid oxide is that it can split hydrogen and CO2 so that you go directly to syngas. As you see, there's quite different characteristics for these different types of electrolyzers. And also the key topics, the key R&D topics that we are addressing are quite different. If you look at the alkaline technology, this is what I always do. If you look at the alkaline technology, which is the lowest cost technology, what we really need to do is increase the power density of the technology and make it suitable for higher pressure operation. The PEM technology reduced the amount of scarce materials and also improved the performance and durability. These are the key topics, and not the only ones. But and if we look at the solid oxide, then scaling up the manufacturing, and we're talking about really thin ceramic materials. It's difficult to scale up. That's one of the key issues in the solid oxide. These are where the technologies are really different. Now let's look at the at how this compares, and these challenges compares to the scale-up ambitions that we have. And what this graph shows is that we have a gigantic task to meet those ambitions. These are data from 2020. Then the estimate was that globally there was about 0.3 gigawatt installed. By now it's around 1 gigawatt is our best estimate. What we see is that we need to scale up to 6 gigawatt in 2024-25, to 4 to 60 gigawatt in where the 60 is the European target, sorry. So to 60 gigawatt, and if we're talking about a mature market, we're talking about thousands of gigawatts. And what that translates to is on the slide there, but that's too far for my pointer to reach. We need to grow by a factor of 125 in capacity between 20 and 2030. And even more if we talk about the far future. So those are really ambitious targets. Now what are the biggest challenges? And I've tried to indicate there's a lot of technical potential to improve the technology, and of course that takes time. But in principle, what is really the issue is the rate in which we have to do that. 2030 is really close. So what are the limiting factors if we want to achieve the goals for 2030? I've noted three main ones: aligning and developing the supply chain, managing risk and how we use data to improve the technology in rapidly scaling up the technology, and development of the energy system and infrastructure. I won't go into that, but of course we need to have the renewable electricity to produce that hydrogen if you want to be able to meet those targets. But let me focus on the first two. This is an overview of from 2020 of the installed, the announced capacity for manufacturing. So where you see gigawatt, you should read gigawatt per year production capacity. What you see is two things from this first table. The first is that there's quite a lot of announcement. If you add it up for 2022, it was 14 gigawatt. So if you compare that to our 30 gigawatt target, that doesn't seem to be the bottleneck. I'll come back to that. But what you also see in this graph, the yellow ones are the Chinese. We see that a very strong dominance on the Chinese on the alkaline technology. Also, by the way, for the PEM technology, there's a lot of investments going on there. And the graphs on the other side give another perspective, namely the different companies working on that. The colorful parts are the alkaline, the lowest cost technology at this moment. The gray ones give the PEM technology investment, and we see those increasing quite rapidly for both. There's quite a break, and I'm showing here the low temperature technologies. If you look at solid oxide, there's quite a lag behind if you look at this kind of capacity. This seems to point towards an optimistic picture. However, if we really look at the supply chain that is needed to produce all those gigawatts, we see that there's quite some challenges. So we see the gigawatt factories being announced, but we don't see yet the supply chain doing the same kind of investment to scale up. And one of the things that really plays a role there is the lack of standardization. It's a really young technology. There's hardly any standardized products, and that makes it very complex for companies in the supply chain to step into this business, as it's hardly clear what the requirements are for the components. That's the supply chain for manufacturing. At the same time, what we see is the supply chain for installing hydrogen capacity. There's a real issue when it comes to safety, and that especially the combination of let's say the common language of permit authorities, of the manufacturers, of the electrolyzers, and the end users and EPCs, and that is really being a bottleneck at this moment. And of course, access to scarce materials. I talked about iridium, but there are other materials as well. And the footprint, what we see, for example, in the PEM, we use PFAS-based materials. We see legislation coming up which may hamper that. Then we're actually trying to scale up very fast, and one of the key issues that we have there is that there's hardly enough time to learn from the first step when we have to take the second step. So what we see is that there's a lot of learnings with let's say first of a kind systems, but already we're scaling up before we have been able to work on those on the issues coming out of those first steps. Availability of infrastructure for field testing is a limitation, and again there's a bottleneck in permitting, and the sharing of data needs to be improved for us to really be able to accelerate. In view of the time, I'm going to go to my last slide. What I've tried to bring across is that there's, on one hand, a gigantic potential to improve the technology. We heard 30 euro per kilogram this morning. That is for the current technology. There's a lot of potential to reduce that, but at the same time, we're trying to do that to improve the technology in a very short time. We see on one hand that there's challenges in the supply chain, but I think one of the key messages is that if we really want to reduce the cost and improve the technology in 2030, we need to increase the learning that we have, and that means that we have to do much more field testing, do this in a much more intelligent way. Our focus has been very much on introducing very large systems, 100 megawatt, 200 megawatt. That's an expensive way to learn. So the key is to improve that. And that's also my call for action. If you look at 42% green hydrogen, it's going to be an expensive goal if we have not taken the time and the intelligence to reduce the cost. So as a community, I would recommend not only to focus on these very large systems, but also look at much smaller scale systems in series where we can really bring down the cost so that that target of 42% can be reached against much lower cost. Thank you.